Last time we discussed air pollution, the causes and consequences of air pollution. This included things like ozone depletion, as well as very high instances of maladies, including cancer, in communities that have historical ties to industrialization, including areas in Louisiana, one such area called Cancer Alley. We also discussed legislation that allowed us to take steps to protect our clean air, including the Clean Air Act of 1963, and then further amendments in the year 1970. So today we're going to discuss something that's very closely tied to air pollution, and that is water pollution. But first, we need to discuss where do we get our water and what are the water resources that we're dealing with on a global scale. So first, we have the hydrologic cycle. This is a cycle that's responsible for distributing water across the globe. Water, as we know, absolutely essential for life. And this water cycle, the hydrologic cycle, endlessly circulates this water throughout the environment on a global scale. So it includes things like evaporation off of the ocean, deposition of that water onto land, and then finally that water returning to the ocean. So taking a look at the hydrologic cycle on a global scale, we know that water and sunlight are unevenly distributed across the globe, and that means different areas in the globe have different water resources available to them. So here we have an image where different regions of the Earth are color-coded by their average annual precipitation. And we see that these more bluer colors are those that experience greater amounts of precipitation and rain, largely concentrated around the equator here. And then those areas that don't see much rainfall, we consider those semi-arid or arid regions. Those are typically found in the mid-latitudes. So it's because of uneven heating of the Earth that we have this uneven distribution of water resources across the globe. So that's how it plays out in space. But as you all know, water can take multiple forms. So we see here in these three pie charts that the distribution of water is often described in terms of interacting compartments in which the water resides. We call those compartments reservoirs. So you can have the ocean reservoir, freshwater reservoir, and then within those nested different reservoirs like ice and snow. So taking a look at the very first pie chart here, we see that we're talking about all of the water on the Earth. Almost 98% of that water is in our oceans. So the ocean is by far the most dominant water reservoir on our planet. And we notice that about 2.5% of all water on Earth is fresh water. But we have to ask, what form is that fresh water in? We see that almost 90% of that is locked away in ice and snow. We have about 12% within our groundwater. And so that means the fresh surface water reservoir that is available to us is really, really small compared to all of the water that we have on our planet. Only about 0.02% of the fresh water is in a form that is accessible to us and other animals. So that is what we have here in this last diagram. So talking about the massive reservoir of fresh water on Earth, we said it's mainly locked up in ice and snow. So that means glacier ice, sea ice, and snow. All of those combined contain most of the fresh water on our surface. About 90% of that fresh water is found in snowfields, ice caps, and glaciers like this one here up in Svalbard. We also, in addition to glaciers that are in the Arctic and in the Antarctic, we also have alpine glaciers, those that are found at a very high elevation in the mountains. Those alpine glaciers and snowfields supply water to billions of people, including here in the United States. But also, what we're facing right now is climate change is altering the amount of fresh water that is available, because glaciers like those in Asia, even those here in the United States, are shrinking because of climate warming. So with climate change bringing about a warming climate, those glaciers and snowfields are shrinking. In places like Tibet, where glaciers supply water to major rivers and drinking water for billions of people, this is a rapidly dwindling freshwater resource that people are scrambling to figure out what they can do. In addition, we also have snowpack on the western slope of the Rockies that provides 75% of the flow in the Colorado River. And so now, unfortunately, that water never even makes it to the ocean because it is such a prized freshwater resource. It is being sucked up before it can make it to the ocean again. And so to drive this point home that climate change and climate warming is having a drastic effect on our water resources, I'm going to play this video.
For us Arizonans, this is where much of our water comes from. Snow falls high in the Rockies, melting and forming small streams. They meet to form larger ones, and further on till joining into the upper basin of the Colorado River.
So it's of great concern to just about anybody in the West, what happens into the upper basin water supply.
That starts with the farmers and ranchers that work the land where the snow falls and it all begins.
We know it's dry. We have, snow melting off early. Temperatures are higher than usual right now. The conversation really becomes more of how we're going to survive this.
The Rossi family has been ranching the Yampa Valley of northern Colorado for nearly a century.
It goes back to the early 20s when my grandpa finally was able to quit working cattle ranches and buy a start for himself.
Philip's daughter Olivia is 9 years old. She knows her way around the ranch.
To get to the goal of her ranching, it's going to take a lot of wise decisions, a lot of good fortune. Hopefully, with the importance of water, that doesn't become the defining moment of you have to sell the place because you can't afford to run the ranch.
We're seeing in a warmer world that runoff is happening sooner. So boom, quick runoff and done.
For ranchers like Philip, this is a problem, as the water is coming at a time when they can't really use it to grow crops. And then late spring, when they really need it, it's gone. It's not just higher temperatures that are causing this earlier runoff.
One of the main issues that we have in the upper Colorado basin is dust on snowpack. It increases the heat load on that snowpack. The snow is going to melt faster than the water enters the streams and the rivers all at once.
As water is heading down from Colorado to Arizona, the dust is moving in the opposite direction.
There are a few source places where it's just constantly producing dust. A lot of it is the Navajo Nation. That fine sand is just something that blows. If you just look at it, then the wind will carry soil particles to the nearest obstruction. And that nearest obstruction will be the mountains.
Climate change was not on our radar. And that was way back when I was 20.
Chris Landry is a pioneering extreme skier. In 1981, he was quoted in Sports Illustrated. The definition of extreme skiing is pretty simple. If you fall, you die. Now, as a snow scientist, he skis into Colorado's backcountry, not for thrills, but to monitor the presence of dust on snow.
This is a change that has occurred in my lifetime. That as a longtime ski mountaineer, having never observed the kind of dust on snow that we're seeing, it's alarming and interesting. We're adding our tiny, small little piece to the puzzle by trying to understand dust on snow.
The demand for water and the availability of water are out of balance.
John Harold is known as the sweet corn king for revolutionizing that crop in Colorado. He also raises cattle and grows grain for the Coors Brewing Company.
We don't have enough water to meet the demand. So how do you balance that? You pray, seed the clouds, put a funnel to the sky, or you use less water relative to efficiency. Water, in my mind, in 10 years, maybe 15, will be more valuable than gold. So it's a resource that we can't live without. Our problem is that we've had plentiful water for such a long time that we don't understand the value of water yet, but we will one day.
So a lot of the available water in the world, including in the United States, is found in groundwater. Groundwater stores large water resources, and in particular, this one in America is the Ogallala Aquifer that we've talked about in previous lectures. And so where does this groundwater come from? So groundwater originates as precipitation or rainfall. That rainfall then percolates or falls down into different layers of the soil, making up the large stores of groundwater that we have. It is very large, and it's also importantly fresh water. So the groundwater within about 1 kilometer of the surface is more than 100 times the volume of all of the freshwater lakes, rivers, and reservoirs that we have combined. So all that goes to point to is how large it is and how valuable our groundwater is because it is in that fresh water form. Let's talk about the different zones of groundwater. First, we have the zone of aeration. So what does that mean? Okay, let's take a look at the land surface here. We have happening at the surface with plants, transpiration that's occurring. We also have evaporation of water from land and water surfaces. We have water runoff, and we have precipitation. So as I mentioned before, the groundwater reservoir is composed of precipitation that falls through or percolates through different layers of soil and rock. So this zone of aeration is that first zone in the groundwater. This is the shallow layer of soil that contains both air and water. So if you'll notice here in our soil profile, we have a number of air pockets, and that precipitation is easily able to move through and infiltrate into this zone of aeration. Beneath that, we have the zone of saturation. That's a lower area of soil that has pores that are just filled up with water. That's why it's called the zone of saturation, because it is saturated with water. This zone of saturation is the source of water in most wells that get put into the ground to extract that groundwater. We have the water table, which is the top zone of saturation that supplies most wells. So deep within the earth, we have geological layers that contain water. And we call those geological layers that contain water our aquifers. These aquifers, they can contain porous layers of sand, gravel, or cracked or porous rock that allow water to be held within those geological layers. So here we have an image that shows the zone of saturation that we were just talking about here. Sometimes you can have the land surface dip into the zone of saturation and thereby allowing a stream or a surface manifestation of the zone of saturation here. We also, when we drill out wells, we have what is called the cone of depression. This cone of depression is created because of the upward sucking of water to the surface, thereby depleting that localized area of water. So that results in a lowering of the water table and this cone of depression. If you notice here in this dry well, the reason why it's dry is because the water table used to sit right here where it says normal water table. It has been sucked up so much so that the water table now has lowered here. So going deeper than the zone of saturation, we see this confined aquifer. Now it's separated by the zone of saturation by what we call an aquiclude. An aquiclude is layers of impervious rock. So that means there's no really short-term direct communication between the zone of saturation here and the confined aquifer. You can drill into the confined aquifers that we have by making these artesian wells that will just continuously flow because of high pressure here. And so these artesian wells have uphill water that provides pressure, that provides a steady stream of flow. And finally, perched water tables result in these natural springs that will manifest on the surface here. So how does our groundwater stores compare to other sources of water on Earth's surface? So first of all, we have to understand that fresh flowing surface water is one of our most precious resources. And we might think that rivers and lakes and streams might be our best sources for those sources of flowing fresh water, but in actuality, rivers contain a relatively small amount of water at any one time. And that's because water really cycles rather quickly through these reservoirs. We compare the size of rivers in terms of discharge, or the amount of water that passes a fixed point in a given amount of time. And so rivers, lakes, and wetlands, they typically are characterized by high discharge rates. So the 16 largest rivers in the world carry nearly half of all surface runoff on Earth. That includes the Amazon River, which carries nearly as much water as the next 7 biggest rivers together. And so that's rivers. Talking about lakes, lakes can contain nearly 100 times as much water as all rivers and streams combined. But what's important about this lake water is that much of this water is in a few of the world's largest lakes. Here we have an image of the Great Lakes in the United States. So the Great Lakes are not only important for the amount of water that they contain, but they also provide sources of food, transportation, and settlement. We also, in addition to lakes and rivers, have wetlands that include bogs, swamps, wet meadows, and marshes. And all of those wetlands play a vital and often underappreciated role in the hydrologic cycle. Another reservoir of water on Earth is the atmosphere. But the atmosphere, although it covers the entirety of the globe, actually represents one of the Earth's smallest reservoirs of water. The atmosphere contains only 0.001% of the total water supply. But despite that small amount, it's still the most important mechanism for redistributing water around the world. What's fascinating is that an individual water molecule resides in the atmosphere for about 10 days on average. We call the amount of time something like a water molecule spends in a reservoir, like the atmosphere, we call that the residence time. So a water molecule in the atmosphere has a residence time of about 10 days. Some water evaporates and falls within hours, so it doesn't experience that full 10-day residence time. Water can also travel halfway around the world in the form of clouds before it ever falls to the surface, replenishing our streams and aquifers on land. So again, the atmosphere is an extremely important reservoir of water on Earth, but it is one of the smallest. So let's shift gears now into water use and what that means for the intersection of resource use and society. So water withdrawal is the total amount of water taken from a water body. And worldwide, agriculture claims about 70% of the total water withdrawal on Earth, and that use is increasing. So here we have an image of a cattle that is taking in some water. I pulled this image from a publication in Animal Frontiers because I was looking for some data on how much water it takes to produce beef. And what I found is that raising a kilogram of grain-fed beef takes more than 15,000 liters of water. You can compare that to raising goats, which requires at least 90% less water than this. So here's a schematic that represents, instead of a kilogram, a pound of beef. And here we have 1,500 gallons of water required to generate that 1 pound of beef. Something that might be considered a dietary alternative is rice. However, rice cultivation, which generally occurs in these rice paddies, takes about 3 times as much water as raising potatoes or wheat. So simply choosing to eat a plant-based diet isn't necessarily solving the problem. You have to be really thoughtful and mindful about what you're choosing to eat if you choose to change your dietary preferences based on water use. So we can represent this in graphical form. And here we have a bar chart that illustrates the water required to produce 1 kilogram of some important foods that you probably consume on at least a weekly basis. So here we have water indicated on the x-axis. This is in liters of water. And here we have corn, potatoes, wheat, soy, rice. So again, this just goes to show you that there is more water being consumed to produce rice than other alternatives, including soy, wheat, potatoes, and corn. Looking at meat products, here's how much water it takes to generate a kilogram of goat, chicken, pork, and beef. So just compare this large amount of water that it takes to raise a kilogram of beef, not even talking about an entire cow, but a kilogram of beef compared to a kilogram of chicken, for example. And then here, this really shocked me. It takes an exorbitant amount of water in order to produce a kilogram of chocolate, which I probably have to reevaluate some things about my life because I really love chocolate, and this is very concerning. But back to that Animal Frontiers article, I found this table that includes different nutritional content comparisons for different food types, and then the water footprint associated with that nutritional content. So again, if you're making dietary considerations, it's not only important to maybe look at, do I want a plant-based or meat-based diet, but also the nutritional comparisons are important. How much bang for your buck are you getting, or how much nutritional content are you getting for the amount of water footprint that is involved? And we also have here the water footprint of 2 different diets in industrialized countries. So here we have animal origin or vegetable origin. It gives you a meat-based diet or a vegetarian diet. Again, with your kilocalories or calories here in the US, we just call it calories, but they're actually kilocalories. Calories per day, and then the liters of day per water needed to produce those calories. So this is just food for thought. Please excuse the pun, but I wanted to provide you some really interesting information. All right. So we talked about agriculture. What else is using water? Well, we have domestic uses and also industrial uses. These industrial uses actually only represent about 1/5 of all the water withdrawals worldwide. European countries use about 70% of water for industry, but less industrialized countries use as little as 5% of their water for industry. A large suck of that water is cooling water for power plants. That is by far the largest single industrial use of water, typically accounting for about 50 to 75% of industry withdrawal. But of course, as we, as a human population globally become more and more industrialized, there is a growing demand for this industrial use of water, including in biofuel production. It currently takes about 4 to 5 liters of water to produce 1 liter of ethanol. So again, in thinking about alternative fuel types, biofuels is something that gets a whole lot of attention, but we might be creating a new problem while trying to solve the known problem. And that known problem, of course, being CO2 emissions, and that new problem being a large water footprint. Something that has gained in recent popularity is a process called hydrologic fracking, or fracking. And so since 2008, This has been a dominant industrial use of water, and this is for the extraction of natural gas and oil from geological layers within the earth. So fracking takes about 4 to 6 million gallons of water to frack one well. And if you've never heard of fracking before, it's simply a way to extract more and more natural resources from the earth. And so the people that frack, they pump water under pressure into oil and gas wells in the earth to help fracture geological formations and release those hydrocarbons that are within the rocks. And sometimes these wells are fracked more than once in order to release additional gas. Now you might be thinking, okay, we're just putting water into the earth. Eventually it should reach the surface, right? And you're right. Yeah, that water does come back to the surface, but it's too contaminated to be reused without a great deal of treatment. The contaminants that are within fracking fluids include known carcinogens like carcinogenic hydrocarbons, as well as some detergents that help in the fracking process. It also includes salts and some radioactive particles that were safely beneath the ground that then get pushed up to the surface. So in areas of intensive oil and gas development, like in Western North Dakota, Oklahoma, Northern Texas, water resources can be severely stressed by the high demands associated with fracking. So now, what about domestic use by everyday households? This includes water for drinking, for cooking, for bathing, for washing, flushing your toilets. Of course, the amount of water used per household is going to vary enormously, and it really depends on your community, if you're in an affluent area or a more rural or poorer area. But the United Nations reports that people in developed countries consume on average about 10 times more water daily than those in developing nations. And so that means poorer countries can't afford the infrastructure to obtain and deliver water safely to its citizens. And this has been a running theme throughout this course as the inaccess to clean drinkable water. Clean drinking water and basic sanitation are necessary, of course, to prevent communicable diseases and, of course, to maintain a healthy life. The UN also estimates that at least 1 billion people lack access to safe drinking water, and 2.5 billion don't have adequate sanitation. So it's not just about having water that's drinkable, but it's also removing that waste efficiently so it doesn't build up where you live. And of course, as populations grow, more people move into cities, and agriculture and industry, they compete for increasingly scarce water supplies. And of course, in these growing areas, water shortages are expected to become even worse. So dealing with water scarcity is something that affects many, many people worldwide. The World Health Organization, or the WHO, considers an average of 1,000 cubed meters, about 264,000 gallons per person per year, to be the necessary amount of water for modern domestic, industrial, and agricultural uses. We can take a look at how people are doing worldwide. Are they meeting that demand? And unfortunately, about 1/3 of the world is below this level for necessary amount of water. We can see by and large where those people live on this diagram here, where we have color-coded the amount of water available in that area, with the bluer colors meaning that they meet those demands for water, and the orange and yellow and pale yellow indicating that they are either water scarce, water stressed, or water vulnerable. You can see by and large that African countries and countries in Asia are either classified as vulnerable, stressed, or water scarcity. So up here in Iceland, if you're curious, nobody has data for Iceland, so that's why it's purple. More than 2/3 of the world's households have to fetch their water from outside of the home, which is pretty interesting. I didn't know that many people had to fetch water from outside of their household. And as you can imagine, that's pretty back-breaking work. I mean, water is heavy, and each gallon weighs about 8 pounds. And this is heavy work done mainly by women and children that can take several hours a day, just going back and forth to fetch water. That could be time otherwise spent going to school or earning an income for the family. However, improved public systems to bring water to families may benefit these poor families in the future. And of course, there are always initiatives to build up a stronger water infrastructure in those impoverished countries.